So this video is going to be about one of my favorite topics, which is entropy. And entropy is so important to the way that we understand our universe. It's the reason why fundamentally time seems to only flow in one direction. We can't go backwards in time. Ice won't ice that melts, the water won't spontaneously go and reform an ice cube, even though we could do that and still obey the conservation of energy. So it's not violating the conservation of energy, which, by the way, is the first law of thermodynamics. But there's this other law of thermodynamics, which gives what we call the arrow of time, this direction. And that is tied intimately in with this idea of entropy. So when we talk about entropy, I think it's helpful to begin with a definition. And a lot of people, when they hear entropy for the first time, they're told that it's a measure of the disorder. And that kind of begs the question, what do we mean by disorder? What number can we put on disorder? And so what I want to do to start off with is I want to talk a little bit more about the nature of entropy, and more specifically what we mean when we say that a substance has high entropy to it. So the equation that we use to calculate entropy, and S is entropy here, is, entropy is equal to some constant K times the natural log of W. And K is Boltzmann's constant. It's a very small number, and it has these units of joules per Kelvin. Those will become important later when we talk about, how entropy is related to temperature. The W is what's called the number of possible microstates. And so again, we have another question. What's a microstate? And so I have an example on this next slide to show you what we mean by microstates, and also to give you a better idea of what we mean when we say something has high entropy. So I have these boxes here. I have two boxes, and I have four particles, which I've just denoted with numbers 1, 2, 3, 4. And I've arranged them in different ways between the two boxes. And what I want you guys to notice is that there's one way that I can have 4 in one box and 0 on the other. Okay. There's also one way I can have 0 on the left box and 4 on the right box. There are a total of 4 ways, so these 3 plus this one, so for a total of 4 ways that I could have 3 on one side, 1 on the other. There's 4 ways that I could have 1 on one side and 3 on the other. And there's a total of 6 ways that I could have 2 on each side. Okay. Now, each one of these is called a microstate. Okay, so a microstate is a specific distribution of particles or energy, and each microstate we could add them together. So if a bunch of microstates give us essentially the same situation, this situation, like the 2 to 2 or the 3 to 1, these are called macrostates. And so we can make a plot of this, and we can plot number of microstates versus, maybe put macrostates on this one, and this will be a bar chart. So I'm going to have, the scale 2, 4, 6. And I'm going to start off with the macrostate of 4, 0. And I only have 1, so I'm going to make a bar. Okay, that's about 1 high. And then I'm going to go to 3, 1. And as we saw over here, there's 4 ways to get that. So I'm going to make a bar 4 high. 4 high right here. I'm going to go to 2, 2 next. And I'm going to have a bar that is, sorry about the bell. I'm going to have a bar that is 6 high. And then I'm going to go to 1, 3, and we're back down to 4. And then over here, we're at 0, 4, and we're back down to 1. Okay, and so we have these bar charts. And what we're seeing is that the macrostate that has the most microstates in it is this one right here. And we would say that this has the highest S. This one has the highest entropy. So when we say that something has a high entropy, what we mean is that it has a high probability of occurring. And we only have 4 particles here. You can imagine the molecules in a room, of like gazillions of them, right? So many. And there's really, and this whole, kind of normal distribution will narrow until we have essentially a peak, just a single peak here, of uniform distribution throughout the room. It's going to be extremely unlikely, although interesting, not zero, it's going to be extremely unlikely for all the gas particles to collect in one space, which would be out on the edges here. So that's fundamentally what we mean by entropy, is probability. Something that has a high entropy means that it has a higher probability. There's more ways to achieve that state than other states. So this leads us to the second law of thermodynamics. And in words, it says for any spontaneous process, the entropy of the universe will increase. So we can say that delta S of the universe for any spontaneous process has to be greater than 0 joules per Kelvin. Okay, now the entropy of the universe is the combination of two entropies. It's going to be the change of entropy of our system, so the thing that we look at, plus the change of entropy of our surroundings. And so we have a situation where we could have a local decrease in entropy. That could be water freezing below 0 degrees Celsius. It could be us. We are extremely low entropy states. But if the entropy of the system is going to decrease, then the entropy of the surroundings has to increase by even more. Okay, and these two things are locked together. So, we can kind of think of like how else can we relate these two? So when we talk about the change of entropy of our surroundings, if we send heat into the surroundings, then we will be increasing. We're going to be putting more energy into it. We're going to be increasing the number of energy states. So we're going to be increasing the entropy of our surroundings. And it turns out, that the change of entropy of our surroundings is going to be negative the heat lost by our system divided by the Kelvin temperature. Okay, so we have this Kelvin temperature and our absolute temperature scale. And so if a system does decrease in entropy, okay, it's going to put out heat very often into the surroundings. And if it puts out heat, remember that loss of heat from the system's point is negative, so we take the negative of a negative and we'll have a positive change of entropy of our surroundings. And so as far as chemistry goes, we can say that the change of entropy of our surroundings will be equal to negative the change of enthalpy of our reaction, because our reaction is a system, right, divided by T. And this is where the whole joules per Kelvin thing comes in. If we have a very high temperature, putting more energy into it isn't going to change the entropy as much as if we had a lower temperature. So when we think about ice freezing, if we have a low temperature, water freezing is an exothermic process, so we're going to be adding heat to it. At low temperatures, I'll draw it out for you. Okay, so water freezing would have a decrease in entropy for our system, being the water. At low temperatures, okay, that change of entropy of surroundings is going to be greater because T is going to be less. Okay, so maybe that will be the change of entropy of our surroundings at low temperatures. And so the net change of entropy of the universe will increase, and it's a spontaneous process. Whereas at high temperatures, okay, so this will be high T. High T, the change of entropy for the surroundings is going to be the same, right? That's not going to change for water freezing. But because we have a higher temperature, the change of entropy of our surroundings is going to be less. We still put heat out into it. It's still going to be a positive change of entropy, but this change of entropy of our surroundings is going to be less. And so the net effect for water freezing at temperatures above 0 would be a negative change of entropy of the universe, which is not spontaneous. And so that's what we see. Water does not freeze spontaneously above 0 degrees Celsius, but it does below. And it has to do with this relationship between the amount of heat being released by the process and the temperature of the surroundings that are absorbing that heat. Now, as I said, this is AP Chemistry. We very specifically want to talk about how entropy is exhibited in chemical reactions. And so one of the things I want you guys to be able to do is to be able to look at a reaction and just tell me whether there's an increase or decrease in entropy for that reaction. So the way you do this is you look at the products and reactants. And if you notice, the products are in a less condensed phase compared to the reactants. So if we're going from solid to liquid or solid to gas or liquid to gas, then we're going to have an increase in entropy. Also, something dissolving like an ionic or molecular compound dissociating or molecules, breaking apart from the solid, that's also an increase in entropy. So if you see that, the delta S for the reaction is going to be positive. Also, if you notice that we have more moles of products than reactants. So say we take H2 gas and O2 gas, and they combust to make water vapor. It's all gas, but we've taken, what would it be? We would have essentially 3 moles of gas, 2 moles of hydrogen, 1 mole of oxygen, going to form 2 moles of water. And so we have a decrease in the number of moles. We have a decreased entropy, or vice versa. If water is dissociating, we would have an increased entropy. So anyway, that's the long and short of entropy, and we'll work with this tomorrow as far as predicting entropy changes in chemical reactions and possibly calculating some entropy changes for some processes. So I hope you guys learned something, and if you have any questions, please let me know.